Now that we've learned about other key operators in the Flux class in Project Reactor, let's take a look at how we can apply these operators in the context of another case study. This case study is case study 2. And in this case study, you're going to see how you can apply various Flux operators in order to be able to create, multiply, reduce, and display big fractions asynchronously. And the operators we're going to be covering here will include create, interval, subscribe, map, filter, take, then, range, do on next, subscribe on, publish on, and various thread pools. Some of these operators we looked at in the first case study, but we didn't look at them in the context of asynchronous processing, which of course is what we're going to be doing now. We're also going to show how the mono from runnable operation can be used. And we're going to use this in order to be able to trigger the displaying of all the results when we've reached the end of our asynchronous processing. So go ahead and take a look at the link at the bottom of the slide to find the code to this case study, and please feel to follow along as I go through my example from my IntelliJ project. We're now inside my IntelliJ IDE, where we're going to examine the source code for case study ex2 relating to the Flux class in Project Reactor. Let's start first by taking a look at the main entry point. As usual, this registers a couple of methods that'll be called back to run, this time asynchronously. And the first method we register is called test is prime timed. And then the second method that we're going to register is called test is prime async. And as the name suggests, we're going to be checking to see whether streams of generated big integers are prime or not. These big integers will be generated randomly, of course. And we're going to use a couple of different variants of doing this kind of processing asynchronously in the background. Because of that, of course, we need to be able to use the async task barrier. As always, we go ahead and register those methods that run asynchronously. When we call the run task method on async task barrier, that will then cause those two methods to be launched in the background, and they will run asynchronously. I'm going to go ahead and start running the methods because they take a while to run. And so let's go ahead and set the wheels in motion here so you can see what's going to happen when the program completes. So it actually takes a while to run. So let me go back over here and we'll let it run in the background for a while. Okay, let's come over here and take a look at the Flux EX class for Flux example. And this will illustrate a couple of really cool points about how to use these advanced Flux features to run computations asynchronously. So let's first take a look at some of the fields that are defined. These are all static final fields. We have the number, the maximum random number to generate, which is going to be 10 million, the number of iterations to run for generating random numbers to see if they're prime. We're going to have 10 of them. We're going to have something called the lower bound, which is the starting point of the randomly generated numbers. As you can see here, the lower bound is going to be defined in such a way where we take the max value and we subtract the number of iterations. And the reason behind doing this is so that we can generate duplicate values. We want to generate duplicate values for reasons that will become clear when we look at the tests. Then we go ahead and create our random number generator, which will be shared between the various tests. The next couple of fields we have here, one of them is something called M prime cache, which is a so-called memoizer cache that maps candidate prime numbers, just randomly generated big integers we've generated, to their smallest factor if they aren't prime, or to 0 if they're prime. And so this is going to be a cache so that we don't have to keep recomputing these big prime numbers to check for prime number primality. Instead, we can just go ahead and look up to see whether or not they're prime. This is a concurrent hash map, and that's because we're going to be running these computations in multiple threads. We define ourselves a sleep duration field, which will be set for ½ a second. And then down here, we define a predicate called S only odd. And this is going to check to see whether or not a number is an odd number. As you can see here, it goes ahead and it mods the number by 2 and checks to see if the result is not equal to 0. So that's how we determine whether a number is odd or not. And then over here, we have a way to generate a big integer. You can see we're going to generate a random big integer, and we're going to do that by simply saying big integer value of with S lower bound plus some random number that goes up to S max iterations. So this is a way we're going to generate a random big integer, which is pretty cool. Okay, now let's go ahead and take a look at the entry point methods into the test programs we've got here. The first one we've got is called test is prime timed. And this will test to see if a stream of random big integers is prime or not by using asynchronous time-driven flux, or a flux stream that's asynchronous and time-driven. So let's see how this works. We use a string buffer here because we need to have thread safety because computations are taking place in background thread and foreground threads and so on, different threads of control. We have a little callback that's used to write the big integer to the string buffer just to make logging easier. And here we go. We're going to start by having the following stream. We're going to use the flux create factory method to make ourselves a timed flux, and you'll see what that does in a second. And that's going to generate a flow of random big integers that are generated at a periodic interval in a background thread. And so we'll take a look at make time flux sync in a moment. It's a factory method. What we get back from there is going to be this stream of random big integers. And as you can see there, we log the next one. We then check to see if that next value is prime or not. Take a look and see how that works in a second. We go ahead and print out each big integer. And this is all taking place in the background thread. And then the final thing we're going to do here is we're going to use the then method, which is this data suppressing operator, with the from runnable method on mono in order to indicate that we want to display the contents of the string buffer, which has been built up by all the other computations. So the basic point here is we're generating events back in the background periodically, and then we're checking to see whether these big integers are going to be prime or not. So let's go ahead and take a look at the make timed flux sync factory method. As you can see, this factory method returns a consumer to a flux sync for big integer. So it uses templates or generics quite heavily. Here's what we do. We go ahead and we say flux.interval, and then we give the sleep duration, which in this case is every half a second. So every half a second, there's going to be a pulse or a signal sent. In this particular case, we're going to completely ignore the value, which starts at 0. And instead, we're going to generate a random big integer. And if you recall, when we had talked about that, that was this little function up here that generates a random big integer between the lower bound plus the random integer that goes up to max iterations. So we're going to generate a value between min and max values just to get some duplicates. You'll see why we want those in a minute. The next thing we're going to do is we're going to filter out even numbers. No sense in checking to see if an even number is prime because it can't possibly be prime. And then we're going to limit ourselves using the take suppression operator to only take S max iteration values. So in this case, that's 10. And then the last piece of the puzzle here, which you can see occurs at the very end of this little flux stream, is to use the subscribe terminal operation. And what it'll do is it'll go ahead and just emit each of these randomly generated big integers that are not even numbers. And that'll then go up through the stream to be processed by the resulting chain after the create method is called. If something goes wrong, we just say we're done. And when we're done, we say we're done. So these are the various signals that can be emitted next and complete to indicate where we are in this generated stream. So if we then go back up here to where this thing is called, we're generating this timed stream of random big integers. And as I mentioned before, we then check to see if they are going to be prime or not. And let's take a quick look at check if prime. It's a very clever little method. What it does is it creates something called a prime result. And a prime result is actually a record. We'll talk about records in a second. And the prime result is going to keep track of the number we're checking to see if it's prime. And then the second parameter we're going to pass in here is the result of calling compute if absent on the concurrent hash map. And what we do is we say, is this prime candidate already in the map? If it's already been pre-computed, if we know whether it's prime or not already, it'll just return the result that was put there before. However, if we have never checked to see if this number is prime, we're then going to go ahead and see if the number is prime. And if the number is prime or not, it's going to get recorded in the map. In either case, we're going to get back whether the number is prime. If it's prime, the result is 0. If it's non-prime, it's the smallest factor that you can use to multiply the number. So that's what prime result is. Let's go take a look at prime result. Prime result's kind of cool. It's actually a Java 16. I think it actually came in Java 15, but I'm using Java 16. It's a Java 16 feature called a record. And a record is essentially just plain old data. It's a pod. It doesn't contain any of the other things that a Java object does. Doesn't have a mutex, doesn't have a condition, doesn't have any other state, doesn't inherit from Java object. It's just basically a place to store data. And in this particular case, the prime result record contains the prime candidate, which is the big integer we're checking to see as prime, and then the result of the isPrime call, which is the smallest factor. Notice the interesting syntax for a record. It looks kind of like a function declaration, but in fact, it's defining a very straightforward data structure. And you also have to put the open close curly braces at the end for syntactic reasons I don't quite understand. Okay, so that's the check is prime method. So that was the first of these methods here, the one called test is prime timed. As you can see, this does it by using processing in the background by the interval factor method that's called on Flux. The next method we're going to take a look at here is called test is prime async. And this is going to use an asynchronous Flux stream with basically some special threads that we're going to define using new parallel. And we're going to have a producer thread, and we're going to have a publisher thread and a subscriber thread. So there's two different threads that are being involved here. That's different from the example we just looked at, that just had the background thread where interval is running. So let's take a look at this code. Once again, we're using a string buffer to store the results in. We have a little log consumer that we can use to print the results. And then we're going to have Flux create, except this time we're going to call a different factor method. This is called make async Flux stream. And we'll look at make async Flux stream in just a second. Much of the rest of the code is the same with one small but important difference. So make async Flux stream is going to end up creating a Flux that'll run in a background thread using subscribe on. So it'll be publishing in one thread. And then we're going to log the results here in the background. And then we're going to switch the subscriber thread. So we're going to use the publish on method and say, I want to run the prime number checking in a different thread, in this case, in the subscriber thread. And that comes out of the new parallel pool, in which case we just have a pool of size 1. And down here, then the map and do on next and then calls will all run in the context of this subscriber thread. So we're going to have one thread where we're publishing data, randomly generated integers that are not even. And then we're going to have a different thread. We're going to be basically consuming or subscribing to the data and processing it by checking to see if the numbers are prime. So let's go ahead and take a look at make async Flux stream. This is a pretty interesting method. You can see here that it uses the Flux sync that we've talked about before. And we're going to start at 1 and go to S max iterations. So again, that's 10. And what we're going to do here is we're going to convert each number to an unsigned long. And that's because Flux lacks a range long method and we need to have things be long. And then we're going to go ahead and use the subscribe on concurrency scheduler method. And what that's going to do is that's going to say, run everything from range to the end to subscribe, run that in a background thread pool of size 1. So it's really just one thread, which we give the name publisher. It's a new parallel pool with one thread, which we call publisher. And what we're going to do in that context is we're going to go ahead and generate random big integers in this background thread using that same generate random big integer that we saw up here before. This is just a function that generates the random big integers. As we did before, we're going to filter out anything that's even to get rid of it. We only want odd numbers to go through this, randomly generated odd numbers. And then we're going to go ahead and use the subscribe method, which is now running in the context of this publisher thread, to go ahead and emit each of these random big integers until we're done. So when we're all done, then we're finished. When we hit the end of the range, we're done. And then the complete signal will be sent to up the stream. So that's how we're going to generate the data here. And as you can see here, that gets done in a background thread. And then that data is then routed to the subscriber thread where we check to see if the number is prime or not. So I think that's pretty darn cool. Here's that check is prime method. Here's the is prime method. This is intentionally designed to be very inefficient, just to burn CPU cycles to make the test run interesting. And this checks to see if if a big integer is prime or not. And I'll let you read the code if you want to see how it works. Here's the process result method. This is what gets called in the logging context, and it just prints out whether it's a prime number or not. And if it's not a prime number, it prints out its smallest factor. Okay, I want to show you what the program looks like when it runs. So we ran it in the background, and it's because it took a little while to run. So here's the first. This is actually interesting. You'll notice that we called the test is prime timed method first, but it actually prints out second. And that's because it's delaying for half a second every time it runs, because it's periodic. It's using the interval method. So this one runs second. You can see what it does is it runs everything in this one thread, and it emits a value, which of course has to be odd. It checks to see if the value is prime, and then it'll tell you whether it found it prime or not. And you can also see that what it's doing here is it's printing out whether it found a prime number or not. And it's also checking to see if the number is already in the cache or whether it has to recompute whether it's prime. So when it doesn't print out checking if blah, blah, blah is prime, it's just looking it up in the cache. And you can see here there's a bunch of duplicates. So that's what's happening with the test is prime timed method. We also have the test is prime async method. And that one is the one that has two threads. So here is the publisher thread. And you can see the publisher thread is running in the background, and it's emitting values, in this case, it's only letting the ones that are odd come through. And you can see that there's some duplicates here. And then the subscriber thread is checking to see whether or not the number is prime. And as before, if it finds a prime number, it says it's prime. If it finds a non-prime number, then it gives the smallest factor for that. And it's using the memoizer cache to avoid having to recompute whether or not a number is prime if it's already been looked up once and stored in the concurrent hash map. So really cool example, very sophisticated example, demonstrates the concept of asynchronous processing, demonstrates the concept of publisher and subscriber threads using subscribe on and publish on, demonstrates how the interval method, the interval factor method, runs in a background thread, as we saw here, which comes out of the parallel pool, which we also had talked about as well. And then we also got a chance to show off that cool recent Java feature called records, which is basically just a plain old data structure that's a little bit lighter weight than using Java objects, because Java objects have to carry along additional state with them in order to implement the monitor object semantics of a vanilla Java built-in monitor object. Okay, so that's basically the end of this example. I very highly recommend that you take a look at the code. You might want to watch the video a couple times because it's kind of subtle, but make sure you take a look at the code, see how it works, and then see how all these things map back onto the various operators that we talked about earlier, especially the ones that have to do with asynchronous processing, like subscribe on and like publish on, as well as the new parallel factory method that makes a pool, which could just have one thread, a pool of one, of parallel processing logic in which to have background threads run in its context.